Hi everyone, welcome back to MATA35. In today's lecture, we're going to be talking about the substitution method. So note that this material isn't actually in your textbook, so I pointed out another textbook and a couple sets of exercises in that other textbook. Those exercises are probably more difficult than what I'm going to expect you to be able to do. However, they are of the right type, and when you look on the practice quiz, you'll see what I expect you to be able to do. Okay, so let's first start by reminding ourselves of the substitution method for integrals. So the whole point of the substitution method for integrals is if we guess an appropriate u, we compute du. So for example, let's say that we started out with some equation y prime is equal to x e to the x squared. Then we compute du. We have to guess an appropriate u. After rewriting it. So I'm going to rewrite it as dy dx is going to be equal to x e to the x squared. And let's have dy is equal to x e to the x squared dx. And so then y is equal to the integral of x e to the x squared dx. So now, as you all know, since you guys have done this quite a few times now, the first thing you do is you let u be equal to, let's say, x squared. So that's our guess. Then you plug that all in. Well, you compute du dx, so du is equal to 2x dx. You plug that in, and you get y is equal to the integral of x e to the x squared dx, which is equal to 1/2 integral of e to the u du. And therefore, when you take this integral, you get y is equal to 1/2 e to the u plus c, and you substitute u back in, or x back in, then you get y is equal to 1/2 e to the x squared plus c. So easy enough, right? And the whole key here is that you just had to figure out what the right u was to make the integral easier to solve. So we can do something very, very similar for ODEs. So the goal here is to convert the ODE to a form we know how to solve. And the strategy is, of course, to guess an appropriate u that's a function of both possibly x and y to simplify the ODE. And as a caveat, sometimes we need multiple substitutions. But let's start with an example. So let's suppose that I have the example where 2y e to the x over y dx plus y minus 2x e to the x over y dy is equal to 0. So what we do is, well, there are a couple ways you could approach this. One is you could check to see if this was exact and try to use an integrating factor. Another way is to use a substitution. In this particular case, we're going to guess the substitution u is equal to x over y. And so that seems like something that appears a number of times. And so this implies that x is equal to uy. But now note that there are a couple different variables here, and so when you take the dx, you actually have to take a total derivative. So dx is equal to u dy plus y du. And now this implies that we have 2y e to the u. You have to plug in dx. So dx here is u dy plus y du. So we plugged in u, we plugged in dx, and this is all plus y minus 2 uy, since x is equal to uy. E to the u dy is equal to 0. Okay? Then the next thing we do is, well, we simplify it out. It turns out that with this particular simplification, we get 2uy e to the u dy plus 2y squared e to the u du plus y dy minus 2uy e to the u dy is equal to 0. These terms cancel out. Oh, can you explain how we got dx again? Yeah, let me finish this up and I'll go back and explain it again. So, but those terms cancel out, and therefore we're left with 2y squared e to the u du plus where was I? Plus y dy is equal to 0. I'm going to divide both sides by y, divide everything by y squared to separate it. So t to the eu du plus 1 over y dy is equal to 0, I'm going to integrate everything. So you could move the 1 over y dy to the other side, but you're able to just, you can do it without moving to the other side and just integrating the two different pieces. So then this gives you 2 e to the u plus ln of natural log of y is equal to c, which, when you plug things back in, is 2e to the x over y plus ln of natural log of ln of the absolute value of y is equal to c. Let's go back. So basically what we did is we did substitutions. But remember, when you had a function of multiple variables, when you take the derivative, when you take a total differential, you have to take the differential with respect to one and then the differential with respect to the other. So here we had, is it just the, yeah, so it's just basically the product rule for derivatives. If you think of both u and y as functions of x. So if you think about this, this is basically saying if you have so it's just basically the product rule. So x is equal to uy. So both u and y are functions of x. So you can think of this as x is equal to some function of x times some other function of x. And then so when you take the derivative of this, so dx when you take the derivative of this, what you get is dx is equal to u dy plus y du. Is that all right? Did that explain a little bit better? So it is basically just the product rule. Okay, so let's go on. So that was a relatively simple example. We had some guess substitution, and then once we substituted that in, we were able to convert the differential equation into a separable differential equation, and then we can just integrate both sides, and then we get the answer. So let me go ahead and give a much more complicated example, and these will be the things that you would actually see in practice. Though things like this probably won't appear too often on quizzes because they take a lot of time. But of course, you'll get problems asking you for parts of these. So for this much more complicated example, let's say we have 2x plus y plus 1 dx plus x minus y minus 4 dy is equal to 0. So there is a multi-step derivation that works for this. So the first thing we're going to do, for reasons that I won't go into too much detail, you're going to substitute u is equal to 2x plus y plus 1, and v is equal to x minus y minus 4. And then you're going to substitute w is equal to u over v. It turns out that after doing both of those steps, we'll have a separable equation. You can solve via integrating both pieces, and you can undo all the substitutions. How we guessed the particular substitutions, I'm not going to get into yet. But let's just see what happens. So this is a more complicated example, and so we are going to have to be very comfortable working with differentials. So the first thing we're going to do is we're going to substitute these two variables in. And when we do that, the first thing we need to do is we need to compute du and dv. So if we have du, well, that's going to be equal to 2 dx plus dy, and dv is going to be equal to dx minus dy. Okay, so just think of it like taking a derivative. How do we know if something is separable again? Something is separable if you can move all the x's into one piece and move all the y's into another piece, or all the u's into. So whenever you have variables, they're all in a single piece together that can be added or subtracted from other pieces, or you can put them on different sides, but they can't be multiplied together or combined in some other way. Okay, so now we have this substitution, and so the first thing we're going to do is we're going to need to substitute all these different pieces. So I'm going to compute what dx and dy are from here, because then I can substitute those in for dx and dy. So the first thing you'll notice is that if you add these two together, you end up with, what is it? Du plus dv is equal to 3dx. And therefore, you know that dx is equal to du plus dv divided by 3. Okay, so that's just adding these two, du and dv together by using the formula above. And then once we have this, we also know that dy is equal to dx minus dv. And so therefore, dy is equal to du minus 2dv over 3. Okay, so that's just rewriting our du's and dv's so that we know what dx and dy are. Well, once we've done that, then the substitution becomes relatively easy. The substitution just becomes u times du plus dv over 3, since that's what the value of dx was, plus v times du minus 2dv divided by 3 is equal to 0. Let's simplify a bit by multiplying on both sides by 3. So u times du plus dv plus v times du minus 2dv is equal to 0. And you end up with u plus v du plus u minus 2v dv is equal to 0. So now, at this point, there are a couple different ways you could try to solve it. One of it is, well, you might think, well, maybe this is an exact integral. And if it is, or maybe you could use an integrating factor. So that's one way of solving it. And we learned how to do it that way in last week. Another way to do it is, however, to do, why is it minus 2dv and not 0? Where is, sorry, in which line? So minus 2dv and not 0. dy is, for dx? Oh, sorry, for dy. So dy is equal to dx minus dv. And so therefore you have, So dy is equal to du plus dv divided by 3 minus dv. But you can think of dv as 3 over 3 dv. And so when you combine together the fractions, you end up with du minus 2dv over 3. Yep. So you just have to make sure that you do all your fractions correctly. Okay, so now, as I said, there are a couple different ways of going from this point. One way is to use an integrating factor or look to see if it's an exact differential. And maybe it is. In fact, in this case it is, so you could actually just use the strategy for solving exact differentials. However, since today's lecture is about substitution, we're going to do another substitution. So, we're going to do list substitution. So what did we end up with? We had u plus v du plus u minus 2v dv is equal to 0. And let's try a new substitution. W is equal to u over v. So note that looks a lot like the substitution we did earlier of x over y. It's just that our variable names are different here. So what we're going to get is u is equal to wv, and therefore du is going to be equal to v dw plus w dv. We're doing the same type of substitution as we did in the previous problem. And when we substitute all these things in, what you end up with is, well, you have u plus u, so that's wv plus v du, but we know what du is, so du here is going to be times v dw plus w dv, and then we're going to add u minus 2v, so u is wv, so wv minus 2v times dv, which is equal to 0. Let's simplify that a little bit. So you get v w plus 1, v dw plus w dv plus v times w minus 2 dv is equal to 0. I'm going to divide by v, so you have to be a little bit careful about dividing by v, because if v is equal to 0, then things don't work. But of course, if v is equal to 0, then your substitution itself wouldn't work either. So we're going to play a little fast and loose with division here. So we're going to end up with, after rearranging things slightly, you'll end up with dw times vw plus 1 plus dv times w squared plus 2w minus 2. I skipped a couple steps here, but basically all I'm doing is I'm doing multiplications and manipulations. So I'm expanding out and then combining everything back together. And you end up with this particular formula. Now, the cool thing about this formula is that this is actually separable. So we can do a separation of variables on this formula. And so let me rewrite it here. dw times w sorry, that's a dw times v times w plus 1 plus dv times w squared plus 2w minus 2. What we want is to put all of the v's in one piece and all the w's in the other piece, and maybe split them on two different sides just to make life easier for us. So what we're going to do is we're going to move the, let's move the dw piece onto the right. So we end up with dv w squared plus 2w minus 2 is equal to minus dw times vw plus 1. Now we can divide out both sides, and we end up getting dv over v is equal to minus dw times w plus 1 over w squared plus 2w minus 2. And now when we do our standard thing, we integrate both sides, and you end up with ln of natural log of v is equal to minus the integral of w plus 1 over w squared plus 2w minus 2 dw, which is equal to, so we need to do a u substitution here. Well, I'm going to use a different variable name, so let's let z be equal to w squared plus 2w minus 2, and so then dz is equal to 2w plus 2 dw, and so then this entire thing is equal to minus 1/2 times the integral of dz over 2. Sorry, not over 2, over z. Which is equal to minus 1/2 natural log of absolute value of z plus c. And therefore, we have natural log of v is equal to natural log of the absolute value of z to the minus 1/2 plus c, and so therefore v is equal to some other c divided by the square root of the absolute value of z. Which we can plug back in, so this is equal to c over the square root of the absolute value of w squared plus 2w minus 2. And let's rewrite this slightly by multiplying by the bottom of the fraction on both sides. So you end up with the absolute value of v times the square root of the absolute value of w squared plus 2w minus 2 is equal to some constant c. Okay, I'm doing lots and lots of steps. You should stop me if you're confused. Basically, I'm just doing standard manipulations. Could you write out the steps that we have to take? Ah, yes. So let's go back to the main slide, which I should have been doing. So we've been doing a multi-step derivation. So the first thing we did is we did list substitution. And of course, you have to compute the du, dv, and substitute in for dx and dy. Then we did list substitution to get, which is what we just did. And it turns out that when we did that, we ended up with a separable equation, which we just integrated. By solving on both pieces. And now the last thing we need to do is we just need to plug in all the variables again. So we just need to undo all the substitutions. So basically, this is just doing lots and lots of integration steps and lots of substitution steps. And we did a separation of variables, and now so we need to substitute everything back in. So again, what we had from the last slide was the square root of v times the square root of the absolute value of, absolute value of v. W squared plus 2w minus 2 is equal to c. Well, we can plug in these values for, plug in the value for w, so you end up with the absolute value of v is equal to the square root of the absolute value of u squared over v squared plus 2 times u over v minus 2 is equal to c. And we end up with this ugly expression at the end of the day, x minus y minus 4, that absolute value, times the square root of the absolute value of 2x plus y plus 1 squared, x minus y minus 4 squared, plus 2 times 2x plus y plus 1, x minus y minus 4 minus 2 is equal to c. So we were able to, after doing all these manipulations, get a closed form expression for, or I mean, not quite a closed form, an implicit expression for the solution to the differential equation. This isn't very nice, but it does give you something that you could plug into a computer. Any other questions? I'm going to have you try it out now with a much easier example. So I'm going to have you try it out with an easy example rather than the super complicated multi-step example. Implicit just means that I don't have y is equal to something. I have x plus y is equal to 0 or something like that. So I don't have an explicit formula for y. So I'm going to have you all try this out. And which of these is the answer? So I'm giving you the substitution here. So the substitution here is x is equal to, u is equal to x plus 2y plus 5. And so let me just get you started, and then hopefully you can solve the rest of it. So the first thing you're going to do is you're going to let u be equal to x plus 2y plus 5. And then, of course, you need to compute du, and then substitute everything in. So for example, this you might want to then compute what x is equal to and what dx are equal to, and so on. And unfortunately, as I mentioned at the beginning of class, Zoom changed their output format for the chat logs, and so my chat voting meter is broken. So you can just put your answer in chat, and I'll read it directly from chat rather than looking at the poll. How do we find x? Well, you want x as a function of u and y. And so you might find x by using that. So if you take u is equal to x plus 2y plus 5, what is x equal to as a function of u and y? So what x is equal to 2y plus 5 plus u? Not quite. So you have to be a little careful because you're subtracting both sides by 2y minus 5, right? So x is equal to 2y, is equal to u. U minus 2y minus 5. Right? So you have to subtract out by this entire thing on both sides. One thing that could be useful to check is you can solve for dx both using directly from the x equation and from the du's equation, and the two answers should match. So you should be able to do lat and lat. So let me go ahead and give you du now. So du is just dx plus 2 dy. And so, of course, that means that dx is equal to du minus 2 dy, which also works if you were to directly take the derivatives with respect to x. And now you just have to plug all these things in. One thing that might be a little helpful is if you notice that 2u is equal to 2x plus 4y plus 10. And so that might help you with plugging that in. Or you can just directly plug it in and you'll get the same answer. So they go to du and dy because we're... Oh no, they're not treated as constants. They're treated as functions of x. And so they're treated as... So when you're doing this, you need to take... when you think about the product rule is d dx of, let's say, yz is equal to y times z prime plus z times y prime. So you could try to do that substitution, but it will not be helpful. So here, you're substituting just to get rid of the x, not to get rid of the y. So you're only substituting in one variable, and so you're replacing one variable with another variable. And so one of the things you need to keep track of here is that's actually a very good point. So thanks for bringing that up. The point of the substitution. So let's see. Point of substitution is to replace one variable. Yeah, so you can think of un minus 2y as both functions of x, and so you use the product rule. Yeah. So here, you're only replacing the variable x with the variable u. And so at the end of the day, you should have an equation that still has two variables, u and y, instead of x and y. Now, if you were to, in the previous example, in one of our substitutions, we substituted for both u and v. So then we replaced both variables with two variables. Here we're replacing just the x variable with the u variable. So let me go ahead and give you the next step of this derivation, which is when you do the substitution, you get u, because that's 2x plus 2y plus 5, times, well, dx is equal to du minus 2 dy, plus, it turns out that 2x plus 4y minus 3 is the same as 2u minus 13. Why is that? Well, you just plug that in, and you'll see that this gives you the same thing. So, okay, so we're getting a couple answers. So people are saying B in chat. Yes, this is correct. It is B. So let me finish solving it for those of you who are still having a little bit of trouble. But when you do this, when you plug this in, you rearrange it, and you end up getting u du minus 13 dy is equal to 0, because the 2u dy's cancel out. Then you take the integral of both pieces, and so then you end up with 1/2 u squared minus 13y is equal to some constant. And so you end up with 1/2 x plus 2y plus 5 squared minus 13y is equal to c. Okay, so that was pretty tricky. You only had to do one substitution, but you still then had to substitute in everything correctly and make sure that you were getting rid of the right variables. So notice when you introduce one single new variable, you can only get rid of one of your old variables. You can't get rid of both of them. In the same way, when we introduce two variables, you can replace both of your old variables with the new variables. So if you had both u and v, as in this step here, then we replace both our variables with x and y with u and v. But when you're just doing a single variable substitution, you can only replace one of your two variables. It actually doesn't matter which one of x and y you replace. I normally replace the first one, but that's just a matter of convention. Okay. So now the question is, of course, how do we guess the correct substitution? And it turns out that like integrating factors in general, there's no good way of guessing the right substitution, but there is a good way in some very specific cases. So the first one is this complicated formula. If you have some differential expression, p of xy dx plus q of xy dy, where the function p times tx and ty is equal to t to the nth power p of xy, and q times q of tx ty is equal to t to the nth power q times xy for some integer n. If this is true, then you can let the variable u be equal to x over y, and you will get a separable variable, a separable ODE. Now, this is, of course, a little bit hard to use. In another class, if you were taking MAT B44, we would actually go through and define these, and in the more general case. Here, more importantly, there's a special case, which is if you convert something to ax plus by dx and ax plus by dy. So if you get rid of all the constants in the sort of linear form, then that satisfies this case, and you can use the u equal to x over y substitution. So that is basically what we did over here. So we used some other substitution and converted it into a form where there weren't any constants inside of each of these. Where there weren't any constants, and each of those only had power 1. In that particular case, you can use this substitution here. So that's one of the substitution guesses. Come on, not there. And of course, there was this other special case, which we did a couple of. So you'll notice that if you had the formula a1x plus b1y plus c1, you can rewrite that, and you set that equal to 0. You can rewrite that as y is equal to minus a1x over b1 minus c1 over b1. And so that actually defines a line, right? And so if the lines defined by the two equations for the two expressions p of xy and q of xy are intersecting, then you do the two variable substitution where u is equal to one line and v is equal to the other line, and that'll give you the case above. And then you can use the other substitution, u is equal to xy, after the appropriate renaming of variables. And lastly, we had a case where if a1x plus b1y, if the two lines are parallel, then you just have to do one single substitution, so let u be equal to one of the lines. Then you'll get a separable ODE. So that was the strategy for the example that I gave you a moment ago. So if you use this substitution here, that's because the two lines are actually parallel. And therefore, you only need to replace one of the lines with your variable, and the other one just becomes your variable scaled to some power minus or plus a constant. And that ends up being separable. And lastly, this is a very common equation that you might see in differential equations classes. This is a will you give us on the quiz? Ah, that is a very good point. I am going to give you this slide on the quiz. So, these are common substitution guesses. I do not expect you to memorize this. I expect you to understand it, but you don't have to memorize it. So I will give you this entire slide on the quiz, or something like it. If you look on the practice quiz, you'll notice that I actually give you like all these statements. So you don't need to memorize what these common substitution guesses are. You just need to be able to recognize what the which substitution you need to do given a particular situation. The last one here is a Bernoulli ordinary differential equation. It almost looks like a first order ODE. And it turns out that if you multiply it by 1 minus n times y to the minus n, and then let u be equal to y to the 1 minus n, then that gives you a linear first order ODE, which we know how to solve using integrating factors. Okay, so these are, and on the quiz, in fact, I'm not going to expect you to be able to solve many of these problems, because these problems are really long and time consuming. So instead, what I'm going to ask you to do is, you should, if you haven't already, you should open up the slide on open up the slide in your browser, or just take a screenshot or something, since on the next slide, I'm going to ask you to guess the substitution. So given this particular example, what is the correct substitution? And if just put the answer in chat, and I'll read off and see what people think. Okay, it looks like most people are saying C. Why is that? Well, if you look at these two lines, you can rewrite this as y is equal to minus x. If you set this equal to 0, then you can rewrite this as y is equal to minus x plus 1, and this one as y is equal to minus x minus 1. And you notice that the slope of both of these lines is the same, but their intercepts are different. And therefore, this is actually a different situation. So because these slopes are the same, you're left in this situation here where you have parallel lines. And so since you only have parallel lines, you actually only need one. So the answer to this one is actually D. You only need one of A or B. Okay, so this was a little bit tricky. Because the lines are parallel, you only need one substitution. Let's try again. So, what about this particular set? X plus y minus 1 and 2x minus y. So again, the question here is, are these parallel lines or are these intersecting lines? Okay, yeah, that's right. So these are intersecting lines, and therefore the answer is C. You need both of these substitutions, A and B. And that will give you, in fact, after you do that substitution, then you'll need another substitution to get it into a separable form. So first step, substitute A and B. Second step, you'll actually have to let some z be equal to u over v. So you need a two-step substitution. But the first step is both A and B. And so that is correct. And then after that, then you end up with a simplified thing that you can do something else to. Okay, and let me give you one last one. So here I have the exponential of x over y dx plus tangent of x over y dy is equal to 0. So what would be the appropriate substitution here? Yeah, so in this particular case, these are one of the easier to recognize ones. If I have a bunch of variables x over y in multiple places, then it makes sense that you may want to have a substitution u is equal to x over y. Okay, so on the quiz, what I will expect you to do is I will give you some equations like these, and then I will expect you to be able to guess the right set of substitutions. So sometimes there will be multiple steps, and sometimes there will just be a single step, but you do some set of substitutions and or guess some integrating factors. So if you look on the practice quiz, let me pull it up quickly actually. If you look on the practice quiz, what I have for you here is I have 6 different equations. I don't know if I'll have a full 6 on the actual quiz. I need to time it and see how long these things take. But then, and I give you basically the slides of how do you guess the second step? Well, in some cases it's pretty obvious because if the two lines are intersecting, then you guess these two variables, right? You'll get this case above, and then you'll need another substitution to get to separable. So once you recognize that these are intersecting lines, then you know the first guess is u is equal to one line and v is equal to the other line, and then the second guess is z is equal to u over v. So you note that on the quiz you will not need to solve the equations. You saw how long solving the equations actually took. I'm not going to expect you to do that. I just expect you to recognize the situation and choose the right guess. If you're in a different situation, for example, if you're in this Bernoulli ODE, then what you need to do is you'll need to, I think I have an extra, I missed a $sign there. I'll need to fix that in a bit. But what you need to do is you'll need to have several steps. You'll need to multiply by this factor. Then you'll need to let then after you do the multiplication, then you need to let u be equal to 1 minus y to the 1 minus n, where n was whatever power was there. That also needs to be an equal sign. So I need to fix the guide. I was typing this up last night, but so this one is incorrect. You'll need to look on the actual slide. Let me go back to the PowerPoint. The PowerPoint slide is more correct. Intersecting lines is the only one that needs two substitutions. So intersecting lines is the only one where you need two simultaneous substitutions. In some other cases, in the other cases that we have, you just need to do a single substitution to get rid of one of your variables. And then sometimes after you do that substitution, then in this particular case, you need to then use an integrating factor, because after you do that, it'll end up as a linear first order ODE. And you will need to remember the integrating factor stuff so I will not give you, that is not stuff I'll give you. Actually, I've changed my mind. I will give you the integrating factor formulas as well. So on the quiz, I will give you both this information, and I'll give you the integrating factor formulas and algorithm, since on the quiz. Okay, any questions about that? Basically, all we have to do here is what we're trying to do is we're trying to transform a equation into another one that is easier to solve. And in this particular part, because solving the equations takes too long, I'm just going to ask you to figure out how to do the transformation without actually having to do it. Okay, let's go back to the PowerPoint. So we guess the substitutions here. Let's finish off this part of lecture with an application, since we've been stuck in math land for a while. So let's go to an application. So let's suppose that we are talking about let's suppose we have a box and we're pushing it. Or sorry, the box has some velocity. We're not pushing it. The box is sitting on some line, and it has some velocity y. And let's say that we have time x. So we're just going to use the standard set of variables. And we're going to figure out how quickly this thing moves, or what speed it has. So we have both drag and friction. And one model of both drag and friction is y prime is equal to minus y plus 0.01 y cubed. Okay? So basically you have some piece of, so drag is weird, and it's some weird third order effect. But in this particular case, we're going to assume that the friction is the minus y, and so this is some model for the velocity as a function of time. And so y prime is the acceleration here, because it's the derivative of velocity, which is acceleration. And so we have this model of drag and friction. Y prime is equal to minus y plus 0.001 y cubed. So now, unfortunately, when you rearrange this, you end up with y prime plus y is equal to minus 0.01 y cubed. This is an autonomous function, but it is unfortunately nonlinear. Luckily, if you'll notice, this falls into the case, once we rearrange it in this way, it looks exactly like, this Bernoulli ODE. And so once you recognize that it looks like your Bernoulli ODE, what you have to do is, well, then we're going to multiply by minus 2y to the minus 3. Because that is the what we're supposed to multiply by, 1 minus n times y to the minus n. Oh, isn't it supposed to be positive? Oh, I think I made it negative everywhere. Yeah, sorry, let me make it negative everywhere. That'll make the math work out slightly easier. Let's make this negative everywhere. Which also makes a little bit more sense for drag, because as you get faster, you have more like wind resistance. So this is obviously a simplified model, but you should think of this, vaguely speaking, as the friction being the standard friction along the surface, and let's say as you go really fast, you end up causing like some weird wind resistance to kick up. Or air resistance, I mean. But let's stay in math land, and so for now, and so we multiply by this value, so you end up with minus 2y cubed. Wait, what did I do wrong here? I think I did something wrong. multiply by to the minus n. So we have minus 2 to the minus 3. Okay, well let's work it out. I think I did my notes wrong, so hopefully this will all still work out. To the minus 3, and we have minus 2. Minus 2y to the minus 2 is going to be, oh, there's also y prime here, which I forgot. And that's going to be equal to 0.02. Okay, so then what we're going to do is then let's multiply, let's separate this out to make it look a little bit nicer. Minus 2y to the minus 3 times dy dx minus 2y to the minus 2 is equal to 0.02. And we're going to let u be equal to y to the minus 2. And then du is going to be equal to minus 2y to the minus 3 dy. And so therefore, we know that du over dx minus 2u is equal to 0.02. Okay, did everyone see what we just did? So we took du, which was this piece here, and we substituted that in. And we also substituted in this u piece here. And so then we were left with du over dx minus 2u is equal to 0.02. Now notice that this is a linear first order equation. It is also separable, but let's use the linear first order formula. Why do we multiply by lat? You're talking about the minus 2y to the minus 3? Lat is one of the various things that Bernoulli figured out, or I don't remember if Bernoulli figured it out or if he proposed the problem. But anyway, this is just a solved problem, that if you have something in this form, you have to, that is just the formula that you use. So I will be giving you that formula. Basically, someone at some point figured out that with this multiplication and this guess, the problem becomes solvable. Yeah, and so I don't expect you to have this memorized. I will give you those formulas. Okay, but anyway, we have a linear first order equation. So then I of x is equal to e to the minus 2x. And therefore, once you use the, so it's a constant. No. So it's not quite a constant. So we have, but the p of x here is a constant. So that's, if you look at the integrating factor formula, you get the integral of minus 2 dx. E to the integral of minus 2 dx. So that's your integrating factor. And if you go back to the formula for a linear first order ODE, you end up with u e to the minus 2x is equal to the integral of 0.02 e to the minus 2x dx. And therefore, u e to the minus 2x is equal to minus 0.01 e to the minus 2x plus some constant. Then u is equal to minus 0.01 plus c e to the positive 2x. And when we substitute this back in, you get y to the minus 2 is equal to minus 0.01 plus c e to the 2x. And therefore, y is equal to 1 over the square root of minus 0.01 plus c e to the 2x. Okay, and this here is now the velocity as a function of time. So it's a little bit hard to see from this formula, but basically what happens is if you start with some positive velocity, well, friction and drag will slow it down. And this is saying exactly how much it slows down as a function of, like, how much it slows down and what speed it's at as a function of time, based on this model of friction and drag. Okay, so having said that, these are a couple of examples. There are a couple caveats. The first one we've already discussed, which is, like integrating factors, guessing the right substitution is really hard outside of a very few known cases, like the ones on the previous slide. In MATA35, I will always give you either the appropriate substitution or provide you with the information on the common substitution slide. So there might be some cases where I give you a problem and I tell you what the substitution is. In other cases, I might give you a problem and then give you the information on the previous slide and just say it's, and then I expect you to recognize that's one of the particular forms, which then gives you the substitutions. And sometimes, like on the quiz, I might even just ask you to guess an appropriate series of substitutions to convert the ODE to a different form, like a separable one or an exact differential. So having said that, this was a, like I said, this material is unfortunately not in your textbook, so I gave you some resources in another textbook to look at. Because this is somewhat more advanced material, but I think it is useful to sort of understand all these different substitutions, since in some ways this is just taking the substitutions from integration and extending them to this problem of ordinary differential equations, which are in some sense a generalization of the integration problem. Okay, so having said that, I think it is about time for a break, so I will stop recording and then I will see you guys at, let's say, 1:10 p.m. And then, oh, sorry, I didn't put my other caveats on here. But yeah, so can you go to the previous slide? Yes, I will go to the previous slide, and I'll leave it on there while during our break. And so everyone be back at 1:15. I will answer some questions, and I might try to get my chat meter back up and running. So, yep.